I'm here again, and I will present our work related to the wearable lower limb neuroprosthesis, in particular the system architecture and control tuning. So, okay, it is not advancing. Now, is it? According to the World Health Organization, around 500 people suffer a spinal cord injury every year, mostly due to traumatic accidents. And the current solutions include the surgery that relieves the patient from pain and the physical therapy. As we can see in this video, it is able to avoid muscle atrophy and able to improve the cardiovascular function. However, as we can see on the movie, it depends on the physical effort from the therapist and their expertise, which leads to a time-consuming therapy. And the current directions have highlighted the potential of neuroprosthesis. It is a robotic device that is based on functional electrical stimulation, and it has been pointed out to create an artificial bypass between the brain and the upper and lower limb function in order to reestablish the motor function for long term. Moreover, this device can be also used as a personalized system, so they are able to recruit the muscles according to the user motor intentions and motor needs. And from the literature, we have verified that this system has been successfully applied to achieve different movements in the upper limbs and lower limb function by using trajectory tracking control strategies implemented by PID controllers. However, we have verified that these systems are non-wearable devices, so they are still not able to be applied for daily assistance. And moreover, we have also verified that the tuning of the PID control, it is a challenge process because it requires a subject and muscle-specific tuning. So it entails a time-consuming tuning processing, and this tuning is also limited by the subject's ability to stand for high levels of stimulation for long periods, which usually leads to muscle fatigue. So in order to overcome these issues, this work proposed two main goals. The first one is to develop a modular and real-time architecture for a lower limb neuroprosthesis, so it innovates by achieving a fully wearable device. And the second goal aims to develop a Matlab-OpenSim framework that enables the fast tuning of the PID controller. And we have also performed the validation during ankle assistance in simulation and real conditions. This framework aims to contribute for a fast subject and muscle-specific tuning of PID control, and it was designed with a modular architecture, so it is able to be applied for different subjects and for different lower limb joints. So regarding the first goal, we have developed this hardware architecture. It includes, as you can see here, the Raspberry Pi, that is a central processing unit that enables data processing and runs the control strategy. It also includes Motion Stim 8. It is a commercial stimulation unit that enables the stimulation of up to 8 muscles. We have also included Inertial Lab. It is a team-made inertial monitoring system that includes up 7 HIMUs, as you can see in the figure, that are attached to the lower limbs by using straps. The system also includes a power bank that supplies all components and allows an autonomy for 4 hours. All these components are inside a backpack to not disturb the user mobility. We have also implemented a mobile application that communicates with the Raspberry Pi by Bluetooth, and this application enables to set some specifications, including the number of sensor, number of stimulation units, to add information regarding the user anthropometric data, and to start and stop the therapy. Regarding the software architecture, we have implemented it on the Raspberry Pi, and it includes 4 main modules. The first one, the central controller, it is able to manage with communication with mobile application to set up the therapy, namely the gait speed, the control strategy, and to include information from the patient, and also to start and stop the therapy. Then the second module, the external device, it manages the communication between the Raspberry Pi and the external device, the stimulation and the inertial lab. And the other model, the controller is able to run the control implemented on this system. And the last model, the monitor, it is responsible to handle with data logging that is being recorded during the therapy. Regarding the second goal, we have developed a Matlab-OpenSim framework that enable a fast tuning of PID control to be then implemented in trajectory tracking control strategies. So we have implemented this framework on Matlab by using OpenSim libraries to run the musculoskeletal model. So the main script, it is able to load the OpenSim model and to enable the configuration of some parameters, including to customize the model according to the user height and weight. It is also enabled to specify the simulation time and to set reference trajectory. Then it runs the simulation every 10 milliseconds. And for that, it executes the simulation function, which gets the joint angle from the musculoskeletal model and compute the PID command based on the joint angle and the set reference trajectory. This PID command is sent to the OpenSim model, so it can update the muscle activation for flexion and extension motions of the joint. After this implementation of this framework, we have used it to tune the PID control for control the ankle assistance using Ziegler-Nichols method, and we have achieved these gains. These gains were then implemented in the real neuroprosthesis system, which includes an hierarchical control strategy organized in 3 levels: the high, mid, and low level control. The high level is not in scope of this work, so we have focused here on the mid and low level controls. The mid-level control includes a regression model that is able to generate a user-oriented reference trajectory according to the user height and gait speed. And low level, it implements the trajectory tracking control strategy by means of a PID controller. So it takes in consideration the reference angle and the measure angle from the HIMU and calculates the pulse width that is then used by the motion stim unity to generate 2 output channels: the stimulation pulse to control the plantar flexion and stimulation pulse to control the dorsiflexion motion, such as the human ankle joint is able to follow this reference trajectory. In this study, we have performed 3 validation phases. The first one aims to validate if the wearable architecture is able to fulfill the real-time requirements. And for that purpose, we have performed bench tests for 10 minutes using the system in maximum operating mode. So to enable the acquisition of the 7 IMUs and the stimulation of the 8 muscle channels. In second phase, we aim to validate the OpenSim, Matlab-OpenSim framework. And for this purpose, we have performed simulation to test PID response to a sinusoidal reference. And in the last phase, we have verified the reliability of the found PID gains in simulation in real conditions to control the human ankle joint. And for that purpose, we have performed tests with a subject in upright position while receiving assistance from the neuroprosthesis. The results for the first phase, we have verified that the call period of the control and data acquisition tasks were able to meet the real-time requirements of 10 milliseconds. So the system, we verified that the system is ready for real-time application. In the second phase, here in the figure, we can see the response of the tuned PID control to a sinusoidal reference, and we have verified that the normalized root mean square error is around 4% and a time delay of 10 milliseconds. So we could verify that the framework was able to present an effective tracking performance. So this framework was not only able to tune the PID control, but it also allows to test PID controllers before their real application in human. So as we have performed in phase number 3, we have performed a real application of this tuned PID control, and from that, results indicate that the system in real conditions presents a normalized root mean square error lower than the one achieved in the literature in the same conditions, and we also have verified a lower tracking delay than one achieved in the literature as well, as you can see. So in conclusion, these works innovates by present a wearable neuroprosthesis, which present an architecture that meets real-time requirements, both for data acquisition and assistance of lower limbs. We have also implemented a Matlab-OpenSim framework that enables a fast subject and muscle-specific tuning of PID control. And we have also verified that using these PID gains found from the simulation, we achieve a more effective and efficient control strategy than one achieved in literature. As future work, we are now working on tuning this and apply this framework for tuning other lower limb joints, and we aim to test it with further subjects. Thank you for your time.
Thank you, Joana, for your excellent presentation. And I think we have time for one question. Yes, one or two questions.
Okay.
Thanks for your second nice talk.
Thank
I
you.
would have a specific question to this OpenSim Matlab.
No, it's not on, but I can try.
It's on, but silent.
Okay, okay.
You said that you use this OpenSim Matlab connection, and maybe you go back to the slide, and then you do some kind of Ziegler-Nichols tuning.
Sorry, can you repeat the last part? Sorry.
Yeah.
Here, yeah, okay.
So your OpenSim is 2D or 3D, the model?
The OpenSim is running this model.
Yeah, but is it a 2D model or a 3D model?
No, this model has 9 muscles for each limb.
Yeah, but the dimension that you simulate?
No, is 3D. Yes.
3D.
Yes.
And why did you decide exactly on OpenSim and not
Okay.
another framework?
Okay.
like
Yes.
Stone
Yes.
or
The OpenSim
Terraform?
is well, it's all open source simulation model for running and performing